Section 5.3 is about the fundamental theorem of calculus. Now, if that title doesn't give you an indication that this is kind of important, I don't know what does. Right? Fundamental theorem of calculus is like the main thing that we've been doing for all last quarter and this quarter. Here we go. Fundamental theorem of calculus. It's going to take us a few videos to get through this. There's two parts of the fundamental theorem of calculus, and they deal with a type of function that you've never dealt with before. So I need to first introduce you to this new type of function. So here we go. Let's take a look at a function g of x, which is defined as the definite integral from a to x of f of t dt. Okay. So somewhere I've got some function f, and let's draw the picture here. So here's the y-axis, here's the t-axis. I've got some function f, y equals f of t, and I'm starting at a and moving over to some other point x, and I'm calculating this definite integral. Again, with the function that I've drawn being positive, this makes it look like I'm calculating area. Okay. Now the thing is, the variable in this function g is being used as the right-hand endpoint of this interval. So the function's always staying the same, the right-hand endpoint's always staying the same. What you're doing is you're just moving, for different values of x, you're just moving to different values here along the t-axis to stop where you're calculating from a to that variable point x. And for different values of x, you're going to get different values for the integral. So there's this new type of function. Okay, let's do an example of one of these and do some calculations to see if we can figure out some values of g given some things here. So just a moment. All right, so here we go. I've got this function here, y equals f of t. I have it drawn this way. This is supposed to be a straight line with slope 1 going up here and then moving over to at slope 0 and then coming back down at slope -2. Okay, so that's my function. I'm assuming that each one of these little blocks is 1 unit. Okay, and I'm going to define g of x to equal the integral. Now the starting point, what I had up here, this a could be any starting point, but once you've chosen that starting point, you stick with it. So I'm going to, for this first example, I'm going to start it at 0 here, and then go to x of f of t dt. Now notice there's an x here and there's t's there. I don't want to use x's in here because when I plug a value in for x, I don't want it to go in here, here, and there. I just want it to go in here. So I'm using this other variable in here. Turns out that other variable doesn't really matter what it is, but well, as you'll see, it's what's called a dummy variable. Anyway, here we go. Let's plug in some values of x to see if we can calculate what they are. So first of all, what's g of 0? Well, g of 0 by definition, right? This is the definition of g. It means you plug a 0 in for x right there, and then you integrate the function. So if you integrate from 0 to 0, you get 0. So in red over on this graph here, I'm going to plot the points that I get. So in red, I'll be doing the graph of g. So g of 0 is 0, which means I'm right here. Okay. Next, how about g of 1? G of 1 is the integral from 0 to 1 of f of t dt. Right? Each time when you plug an x in, whatever value of x you plug in, it's being used as the right-hand endpoint of the interval you're integrating over. Okay? So what is the integral of this function from 0 to 1? From 0 to 1, I'm looking at a triangle there. Has base 1, has height 1, so that must be a half. Okay? I don't need to do any Riemann sums at this point. It's a geometric object that I know how to find the area. when I go from 0 to 1, this height function being a straight line is giving me a triangle, and I'm calculating that area underneath, and that area underneath turns out to be half. So what is g of, what just happened here? What is g of 1? It's a half. So I'm going to plot that point right here. G of 1 is a half. And it didn't like me, so there we go. And it's still not liking me. Yay, G of 1 is a half. Now let's try G of 2. And I'll just stick in red for now. So this would be the integral from 0 to 2 of f of t dt. Actually, notice that I say it doesn't really matter what the variable is, because by the time you've calculated the area, the variable's gone. I could have said f of q dq, or f of smiley face d smiley face. Whatever that variable's called, you're doing an area calculation, and you're coming up with a number anyway when you're done. So 0 to 2 now would be the area from 0 to 2 underneath. I got a bigger triangle. Actually, what I see is that I have all the area that I used to have, plus I can just count the squares here. I got a whole square and then a half a square. So I'm at a total of 1 and 2 halves. So I'm at a total of 2 now. Looks like this is equal to 2. Wow, come back. So I'm going to be plotting right there. All right, let's try G of 3. G of 3 is the integral from 0 to 3 of f of t dt. Well, if I integrate from 0 all the way out to 3, now I've got this bigger triangle. Actually, I have the same little triangle I used to have, plus 1, 2.5 more. So I must be up at 4.5 at this point. 1, 2, 3, 4.5. Maybe you can see that when I go to G of 4, well, G of 4 is the integral from 0 to 4, so clear out to here. I'm looking at a triangle that's even bigger, but it's the little triangle, well, it's this triangle that I had, plus 1, 2, 3.5 more than that. So a half, 1, 2, 3 more than that. So now we're up to 8. G of 4 is 8, is that right? If I look at the area of that triangle, 4 times a half is 8. Right? So for this stretch, the graph is looking something like, kind of looks like a parabola. Then, G of 5. Well, by the time I get to G of 5, by the time x equals 5, you've got that whole triangle plus the area here, right, in that rectangle. So all the area I used to have plus 1, 2, 3 more. I'm just counting the squares. Each of these squares is 1 by 1, so area 1 in it. So I was at 8, so 9, 10, 11, 12. And I'm up to here. And then I'm go over 1 more, and I gain 1, 2, 3, 4 more squares, so I'm up 4 higher. 1, 2, 3, 4. This actually looks like it's going up like a straight line now, with slope 4. Then, moving over to here, again, I'm integrating each time. I'm always starting at 0 and integrating over to whatever value it is. So I'm up to, so 4, 5, 6. I'm up to x equals 7 now. So I had all the height I used to have, plus 1, 2, I don't know if it's obvious that those two pieces add up to another one. So I'm adding another 3 onto that. 1, 2, 3. And then by the time I get over here to 8, I'm adding on another 1 to that. And this comes in like that. Okay. So that graph right there in red is y equals g of x. I'm calculating the area underneath f, always starting at 0 and ending at whatever value of x you tell me to stop at. Okay, and then I'm graphing that result as the y value for g. Okay, so this function, this g of x, is an area function underneath f, and the variable is the right-hand endpoint. You're integrating from a out to x.